Okay, so I want to discuss dynamical degrees. Okay. So this has already been introduced last week by Charles Favre, but at least in the beginning I won't refer to his talks. And I want to discuss two topics concerning dynamical degrees. In the first part, this will be dynamical degrees and relationships to topological entropy. And the second part, which will be disjoint from the first one, will be semicontinuity. Of dynamical degrees. When you have a family of rational transformations that depend on a parameter, and you want to know how the dynamical degree of the transformation varies with the parameter. Okay, and we will show that the variation is lower semi-continuous in the Zariski topology. Okay? So that will be the goal. So for the first two lectures, I will consider topological entropy, and for the last ones, I will talk about semi-continuity and why it is important for dynamical degrees. So first, what is topological entropy? Okay, so it's a topological notion. It has nothing to do with algebraic geometry, and I want to define it and then compare this notion to the notion of dynamical degree. So, okay, so what is the definition? So you start with X. X is a compact metric space. And you give yourself a transformation of X, so a map from X to X, which is continuous. Okay, so I just write C0 for continuous. So I will use the metric defining the topology on X. So I will denote it by distance between 2 points. But at the end, the notion I will introduce, the number I will introduce, will not depend on the distance. By this, I mean that if you choose another distance which induces the same topology on your compact space, then you will get the same number. Okay, so now you fix a epsilon, which is a positive number. You fix it. And you want to observe the dynamics of your transformation at scale epsilon. So if 2 points are at distance less than epsilon, you don't distinguish them. They are the same for your observations. Okay. And then you want to count the number of orbits that you can see with this precision when the time runs between 0 and n-1. So you allow n steps in your dynamical system. Okay? So before I do that, maybe I should recall what are orbits, iterates of a map, periodic orbits, so basic things like that. Okay. So, but the goal is to estimate the number of orbits that you see at scale epsilon. Okay, so first I recall what I mean by orbits or trajectories of a point. So if you start with a point X in X, the orbit of X under the dynamics given by F is the sequence of points x, and then f of x, and then f of x, etc. So it's the sequence of points fn of x, where fn is the nth iterate. Okay, so it's f composed with f n times. So that's the orbit of x. Okay? And you say that x is periodic if its orbit is finite. So if x is preperiodic, the drawing is as follows. You start with x, and then you map by f, you get f of x, and then you do it again. So each arrow is what does f to the previous point. And because the set is finite, at some point you go back to the same point. So typically you get something like that. Okay, so a preperiodic orbit is made of two parts. There is some kind of initial behavior that happens only once. And then later on, you get a periodic behavior. You go back always to the same point. Okay, so you say that x is periodic. If there is some integer n, at least one, such that fn of x is equal to x. Okay, so for instance, this point, f2 of x, is periodic of period 4. Okay, so the period is the minimum number n such that this equality is satisfied. Okay, so let me come back to what I meant here concerning counting the number of orbits. So as I said, I fix epsilon positive. Now I fix n. And I say that x and y have the same orbit during time or period n at scale epsilon. So you see, I cannot distinguish their orbit if I make at most n observations at scale epsilon if the distance between x and y is less than epsilon, and then the distance between f of x and f of y is less than epsilon, up to the nth time of observation, which means that I iterate n minus 1. Okay. So all first n observation gives you similar points at scale epsilon. So equivalently, you can look at the distance dn of x and y is the maximum for j between 0 and n minus 1 of the distance between fj of x and fj of y. So here, f iterated 0 time, for me, is just the identity of x. Okay, so this is a new distance, which is what you get when you iterate the map. And x and y have the same orbit. I mean, I don't repeat it, but up to time n minus 1 at scale epsilon, if the nth iterated distance between x and y is less than epsilon. Okay? Okay, so now you count the number of orbits. So you can define capital N at time little n at scale epsilon is the number of orbits you see during this time n at scale epsilon. So how do I define it? It's the minimum of the number of balls of diameter of, radius epsilon that I need to cover x. Okay, and these balls are with respect to what? With respect to this metric dn. What does it mean? It means that you have to find a generating set. So let's say S in X is generating for n epsilon if for every y in X there exists X in S such that the distance between fj of x and fj of y is less than epsilon for every j between 0 and n minus 1. Okay. So if you have such a generating set, the meaning is that the orbit of y is similar to the orbit of some element x in S up to time n. Okay, and then you can cover x with the balls of radius epsilon centered at the element of S. And so this gives you such a covering by balls of radius less than epsilon. So the balls for the metric dn centered at x and of radius epsilon with x in S cover capital X. Okay. And so what you are counting is the minimal size of such a set S. So the minimal number of points you need to follow all possible orbits at scale epsilon up to time n. So this is the number we are interested in. And then what is the entropy? The entropy counts the exponential growth rate of this type of numbers. So you define the topological entropy of f at scale epsilon to be the supremum limit and as n goes to infinity of log of this number of orbits divided by n. And then you let a precision go to infinity, which means you let epsilon go to 0. So when epsilon becomes smaller and smaller, this quantity increases. So here you can put a limit. Okay, you see, it's completely topological, okay? There is no algebraic geometry. It's just dynamics of continuous maps. Okay, and you can do as an exercise the following thing. First, the topological entropy does not depend on the distance. Okay. By this I mean that if you take two distances okay, dist and dist prime, defining the same topology, then you get the same value for entropy. If you compute the entropy with the first distance or the entropy with the second distance, then you get the same number. Okay. This is because X is compact and you are inducing a topology of a compact set, so there are some uniform controls between the two distances. Okay, maybe I just give one exercise. Okay, so now what I want to do, I want to give examples. And then I want to explain that for regular endomorphisms of complex projective varieties, then we know how to compute topological entropy in terms of dynamical degrees. This is what I want to do. And I insist seriously, okay? And I will do it again tomorrow, I guess. So there will be a formula that for, more generally, for holomorphic transformations of compact Kähler manifolds, the topological entropy is equal to the log of the largest eigenvalue that you see on cohomology. This formula is really hard to prove. And some people, they say, okay, because of this formula, I look at the largest eigenvalue on cohomology, I take the log and I call it entropy. And now I do it for all maps, even for endomorphism of projective varieties which are defined on a finite field. Okay. And this is completely wrong. You should not do that, okay? It does not convey the right feeling of what entropy is, okay? You can call it algebraic entropy if you want, but not entropy or topological entropy, okay? And I will insist on that because it's really important. Okay, so let me give examples. Okay, example one. You take X to be the circle. Okay. For me, the circle is just R mod Z. Here you can think about it as exponential 2i pi theta in R mod Z. And you look, or if you prefer, it's also complex numbers with modulus equal to 1. Okay. And then you look at the map. So you pick D larger than 2, and you take F of Z to be Z goes to Z to the D, viewed on the unit circle, or if you prefer, theta goes to D times theta modulo 1. Okay, so take 2 points on the circle. Okay, and fix epsilon. So let's say fix epsilon small. I will take it less than 1 over d, maybe 1 over 2d. So when do theta and theta prime have the same orbit during time n at scale epsilon? So at the starting point, you need the distance between theta and theta prime to be less than epsilon. But then what happens? So let me draw a picture here. So you have some theta and theta prime. Let's say here it's theta equals 0, which is just a 0.1 in C. So at the beginning, they have to be close. But then you apply the dynamics, and so what you do is you multiply theta and theta prime by d. So this distance is multiplied by d. Okay. So this is why I assume epsilon less than 1 over d, because I want them close enough such that the map multiplication by d does not cover several times the circle. So then you need theta minus theta prime less than epsilon divided by d. Okay. And then you iterate. Okay. And so at the end, you need theta minus theta prime less than epsilon to the divided by d to the n minus 1. And this means that theta and theta prime have the same orbit, okay, at scale epsilon up to time n. So this is exactly the meaning of this definition that I introduced. Okay, and then how many? So what is the ball of radius epsilon for this metric dn? It's just the interval of radius epsilon divided by d to the n minus 1. Okay, this last assumption, I mean constraint, implies the previous ones. So to compute the balls, you just have to compute this interval. And how many intervals like that do you need to cover your space x? So the length of x is just 1, and you need to cover it by intervals of size epsilon divided by d to the n minus 1. So you need roughly d to the n minus 1 times epsilon such intervals. Yeah. So you end up with the following formula. This number n capital N, the number of orbits at time n scale epsilon is roughly d to the n minus 1 divided by epsilon. And this implies that the topological entropy of F at scale epsilon, so you take a log divided by n, it's equal to log d. So this does not depend on epsilon, provided that my argument works. For instance, if I take epsilon to be 10, larger than the diameter, I see nothing. Okay, so I have to take epsilon small enough. So it was what? It was less than 1 over 2d. So this gives you a formula for the entropy. Okay. Now let me give an exercise. First, show that if f from x to x, so x here now is any compact set with a metric, is an isometry for the distance, then the entropy is 0. And then let me state a second exercise which will imply the first one when X is a manifold. Assume X is a compact manifold of any dimension, and say that, and F is a Lipschitz continuous. So this means that a distance between f of x and f of y is less than some number which I call the Lipschitz constant of f times the distance between x and y for any xy. Then the topological entropy of f is bounded from above by the dimension of x. So this is why I assume that it's a compact manifold. It's to talk about its dimension times the logarithm of the Lipschitz constant of f. And a third example or exercise is that if X is a product space, X1 times X2 times Xk, and F is diagonal, okay, so by this I mean that I have K compact spaces, Xi, and for each of them I have a transformation Fi of Xi, which is continuous, and F is just acting diagonally. Then the topological entropy of F is just the sum of the entropies. Okay. Okay, so you see this this second statement here in the case of multiplication by D on the circle, we obtain a case of equality. The circle has dimension 1 and the Lipschitz constant is D. Okay. Taking product maps, you get examples of equality in any dimension. Okay, maybe I give one more example. I want to give an example with an invertible map. So let's say it's example 2. You take A to be the matrix 2, 1, 1, 1. So it's in SL2Z, the integer coefficients, the determinant is 1. The eigenvalues what are the eigenvalues? You see the determinant is 1 and the trace is 3. So there is one eigenvalue larger than 1 and one smaller than 1. And these are 3 plus square root of 5 divided by 2. And it's Galois conjugate. So this is lambda. And this is 1 over lambda. Yeah. Okay, so it's just a linear map of the Euclidean plane. But now you observe that the lattice Z2 in R2 is invariant under A. So A acts on R2, preserving the lattice Z2. So I can take a quotient of R2 by Z2, and I get a torus, a two-dimensional torus, and A will induce a transformation of this torus. So I get the following diagram, R2 to R2. A takes the quotient, and here I get a transformation F index A. Okay. So F index A is a diffeomorphism. In fact, it's the infinity or analytic of R2 mod Z2. So of a torus like that, which is a circle times a circle. Okay, so now I want to describe a little bit the dynamics of this map so that you get an example in which you understand periodic points, entropy, etc. Okay, so first, what are the periodic points? Periodic points are exactly the elements xy in R2 mod Z2. So I denote by x and y the coordinates in R2, which have rational coordinates. Why is it so? Because if you take x, y with rational coordinates, you can write x to be a divided by k and y to be b divided by k, where k is let's say the product of the denominators of x and y. So you can put x and y at the same denominator. And the set of points like that is finite. If you fix the denominator, you have k to the square points like that. And these points are permuted by a map with integer coefficients. Okay, so these points, they stay in the same finite set, so their orbit is finite. And because f is invertible, their orbits are periodic. Okay, so points like that give periodic points. And conversely, when you look for periodic points, you have to solve the equation a to the period of xy is equal to xy modulo z square. Okay. So you have to solve a to the q minus identity of xy is in z square. Okay. But this matrix, when you iterate, so q is some period, some positive integer, this matrix, the eigenvalues are lambda to the q and 1 over lambda to the q. So this matrix, when you write minus identity, is a matrix with integer coefficients which is invertible, in the sense that the determinant is not 0. An invertible matrix has a matrix with rational coefficients. So when you invert, you say that x and y must be a rational number. It's the inverse of this matrix applied to integer coordinates. Okay, so this shows the first point. And this first point implies that periodic orbits are dense in R2 mod Z2 for the usual Euclidean topology. Okay, so second property, I will not prove it, but let me state it. There are dense orbits. So you can find points in your torus such that the orbit of the point is dense in the torus. And there are orbits whose closure is a Cantor set. So orbits can be closure of orbits may have different natures and be very interesting subsets. And there are many more examples. And 3, the topological entropy of F is equal to log of lambda, log of 3 plus square root of 5 divided by 2. Okay, so I will not prove the second property, but the second property, you can do it as an exercise. So before doing it for this type of transformation, do the same thing for multiplication by d on the circle. Okay, so for instance, if you take multiplication by 10, it's very easy to understand this transformation if you write theta in given by its decimal expansion. If you look at multiplication by 10, it's just you multiply by 10, so you translate the decimal expansion by one place. I mean, the comma is moved to the right, and it's modulo 1, so you can forget about the first coordinate in your decimal expansion. So it's just a shift in terms of coefficients of the decimal expansion. So this type of property is very easy to prove in this example. Okay, so these are the types of transformation that occur in this setting. And in fact, the 2 examples I gave are also examples of algebraic transformations. Okay, z goes to z to the d is, of course, a polynomial transformation. And this linear map on the torus, you can cook similar examples on a billion varieties, or you can look at monomial transformations, and you get similar examples. Okay, so this type of behaviors, they occur in algebraic dynamics. Okay. So what was my numbering? Okay, this is what I wanted to say concerning topological entropy. Now let me do a second section or paragraph. Okay. Okay, here is the theorem. So I take M will be a compact manifold. A compact connected manifold. And I denote by H star of M, let's say with integer coefficients, it's the cohomology of M. So here I don't need to use integer coefficients, so let's say I take real coefficients. Okay, so you can think about it as a singular cohomology or the RAM cohomology, what you prefer, okay? But what you just need to know is that given M, you can associate real vector spaces of finite dimension to M, such that if F acts on M, the continuous, then F induces linear transformations on the cohomology of M. Okay. So I put a star because I don't want to make the, let's say the codimension precise. It's just a sum for k between 0 and the dimension of M of HK MR. So you can take, for instance, the RAM cohomology, and you say that HKMR is given by differential form of degree k, which are closed, modulo exact ones. And here it's the pullback on differential forms. If I do that, I need to assume F is C1, let's say. In any case, I will assume that F is smooth. Okay, and then when you have a linear transformation of a finite dimensional vector space, you can introduce its spectral radius. I will denote it by rho of F star. Okay, so what is it? So if F from V to V is a linear transformation of finite dimensional real vector space, okay, or complex vector space, you define rho of F to be the maximum of the eigenvalues of F. Okay, so let me be more precise. Alpha is an eigenvalue of F on the complex vector space associated to F. Okay, so V sub C is just V, which is a real vector space, and you extend the scalars to C. So this is just to say that I consider all possible eigenvalues of F computed in C. And then you take the modulus of such an eigenvalue, so you get a finite number of real numbers, and you take the maximum. Okay, so this is the spectral radius. In other words, you compute the characteristic polynomial of F, then you compute the roots in C, you take the maximum modulus of the roots. And this is also the limit, and as n goes to infinity, of what? So you compute the norm of the nth iterate of F, and you take the nth root. Okay. So what is this norm? You put any norm on V. If you have a norm on the vector space, you get a norm on the space of endomorphisms, and you compute the norm of the nth iterate, and you take the nth root. In finite dimension, all norms are equivalent. So if I change the norm, I will just, they will be comparable up to a multiplicative factor, and since I take the nth root, this does not change the result of this computation. Okay. Okay, and what is the theorem of Yomdin? So let F be smooth transformation of a compact manifold. And when I say smooth, I mean infinitely many derivatives. Okay, so M is a compact manifold which is smooth C infinity, and F is smooth C infinity. Then the topological entropy of F is bounded from below by the logarithm of the spectral radius of F acting on the cohomology of M. So it holds for all compact manifolds and all smooth map but you have to assume C infinity. If you put C1, this is Schub's conjecture, and this is not known. We don't know whether it's true or not. Yeah. Oh, I mean, if you put CK, finite K, we don't know. Okay, it's really a difficult theorem. Okay. And the proof, in fact, is much more interesting than the theorem itself. It tells you a lot of things concerning real algebraic geometry, for instance. Okay, so I want to sketch the proof of a theorem which was proven before that, and which is simpler. It's a particular case of this theorem when you don't look at all eigenvalues of F star on all possible cohomology groups, but you just look at the eigenvalue that appears on the top cohomology group. And this eigenvalue is a topological degree of F. Okay, so you take such a map. Here you just need to assume that it is C1. Then, if every point x in M has at least k preimages, under F, okay, so for every x in M, there are at least k distinct points which are mapped to x by F. Then the topological entropy of F is bounded from below by log of k. Okay, so if M is orientable, then its fundamental class is multiplied by the topological degree of F, by the action of F star on the top cohomology group. And this implies that every point has at least k preimages. Okay. So in particular, the topological entropy is bounded from below by the log of the topological degree. Okay. So I want to sketch a particular instance of this theorem to explain ideas that come in this setting. So first, I will do it when F is a covering map. Okay, so when the differential of F, so this is a tangent linear map when it is invertible for any x in M. Prefer when F is étal. Okay. So in that case, for every x in M, there exists an open set such that F restricted to this open set okay. So it maps Ux to some Vx, which is also open, and this is a diffeomorphism. It's just, how do you call that? Local inversion theorem, okay? Or implicit function theorem. Because the differential is invertible, I can invert the map. So in particular, there is an epsilon. Okay, so here I will discuss topological entropy. So I put a metric on M. In my mind, I put a Riemannian metric and I put the distance associated to this metric. Okay. So locally the map is a diffeomorphism, so locally the map is injective. Okay, and because M is compact, this is uniform. Okay, there is an epsilon, which is positive, say epsilon 0, such that F is injective in restriction to every ball of radius at most epsilon 0. Okay, it's a local diffeomorphism, so locally it's injective. Okay, so this is what I will use. And now I want to show that there are a lot of orbits. Okay, so I fix epsilon less than epsilon 0. And I fix a point Z in M. And then I take the preimages of Z. So I take K of them. I know there are at least K of them. So take K distinct points xi such that f of xi is equal to Z for every I. So maybe I will use slightly more precise notations. So I will do an iterative process. So I'm doing at step 1, and I denote my points by points at step 1, so x1 of I. Okay, so I have a point Z, and then I have x11, x1i, etc., and each of these points are mapped to Z by F. And because the map is locally injective at scale epsilon 0, it's locally injective at scale epsilon, and so the distance between these points is more than epsilon. Okay? If I take 2 points in this fiber of F, because they are distinct and mapped to the same point, they cannot be in the same ball of radius epsilon, so the distances here are more than epsilon. So let me. The distance between these 2 points, any two of them is more than epsilon. Okay, so now do it again. So I have point Z. I have the point x1i. And for each of them, I take k distinct points which are mapped to it. So the arrows explain what F does. Okay. And so I do it here again, etc. And so this is step 2. So these are points obtained at step 2. I label them like that. So here I had k points, and here now I have k to the square points. Okay? Because I had k points. At each step, I know I have at least k preimages, and I choose k of them. Okay? Okay. Okay. So this one goes here. Okay. So these points are distinct. I mean, the preimage of one given point is made of k distinct points by construction. And maybe this one and this one are equal, but not because this one is mapped here and this one is mapped here. Okay, these points are distinct, so their fibers are disjoint. Okay, because for any map it's like that. Okay, thank you, Alex. Okay, and then I do it again, and I do it n times, or n minus 1, I never know. But if I do this process n times, I get k to the n distinct points. Okay, so I have, I take the set S, which is the set of points I get at step n. Okay? And now what I say is that 2 points in this set have distinct orbits at scale epsilon in time n, or maybe n plus 1, but n is okay. Why is it so? Okay, so the fact the n orbits of the points in S, n is for iterating n times, in S are distinct or distinguishable at scale epsilon. This means that if I take 2 points in this set here, okay, I look at their forward orbits, it's not possible for them to always be at distance less than epsilon. So here, this is what Alexi said. So Alexi's remark was, oh, maybe the 2 points here can be equal. Or no, because they are not mapped to the same point. But what could happen is that maybe 2 points are very close, are epsilon close. Okay? So this we need to be careful with this possibility. Okay, so you prove this by recursion on n. I proved it for the first step. Okay, this is what I said before. The distance between this point in the first fiber is less than epsilon. Okay, so now let me prove it by recursion. Assume I have 2 points here at the starting nth fiber, which are n epsilon close. So epsilon close for the nth first iterate. So they are close at the beginning, close, close, close. And here, when I arrive here, they must be epsilon close too. But then this means that they coincide. And so I look, instead of looking at the whole picture, I just look at the picture starting from this point where they coincide, and I apply the recursion. Okay, so this is by recursion. Okay. So by recursion on n. Okay, so I'm done because I have proven that to cover my space by balls of radius epsilon for the distance dn, I need at least a number of elements in S. So I have proven that n epsilon is more than k to the n. And you take logarithm, you divide by n, you take the limit, and you get what you want for entropy. Okay? So this is a sketch of the proof. In the case when the differential of f is everywhere invertible. Okay? So this is the easy case. So now I will just wave my hands. What can you do when this is not like that, when the differential of f vanishes somewhere. Okay. So you apply the same strategy, but from time to time, it may happen that a pre-image is very close to the set where the differential of f is not invertible. So this is where the Jacobian determinant vanishes. Okay. So you do it if I find, let me do it here. If I find k pre-images, I mean, if all the pre-images are, let's say k of them, are far from the set where the Jacobian is 0, then I keep them. If I'm not able to do that, I just take one pre-image, and I continue. Okay. So my process now has two possibilities. Either I find k pre-images which are good, far from where the Jacobian is 0, or I don't find them, and so I just take one pre-image. Okay. So, and you do this computation. Okay. So you are in trouble if the bad transitions, when you choose just one pre-image, occur frequently in this process. Okay. But a bad transition corresponds to a point all of whose pre-images are near the Jacobian determinant being 0. And you compute the volume of this set, and you show that, in fact, the volume has to be small. And so you can find a point Z with almost all transitions which are good. Okay, so this is a little bit technical, but easy once you know what I said. Okay? Okay, where am I? Here. Okay, so now I just want to make one remark. Let's say, give an example to show that smoothness is important. Okay. You take the Riemann sphere, say C bar is C with a point at infinity. And you take the map Z goes to, let's say Z is exponential to I pi theta times some, let's say, radius R. And I map it to 1/2 of exponential 2I pi. And now I double the angle. No R. That's the point. Okay, so this is Z square divided by the, well, I can put a R. Yeah, I can put a R if you want. This, it doesn't matter much, okay? Yeah. I can put a R. Yeah, it's much better to put a R. I want it to be, sorry. I wanted to put a R, okay? Okay, this is this map. Okay, so you see, if you forget about that and just look at what's happened on the theta parameter, that's why I was forgetting about the R. I was focusing on this one. You see, you just double the angle. Okay? So at the level of what happens on the theta parameter, we already studied what happened, and it seems the entropy is log 2. Okay, logarithm of the degree by which I multiply. But on the other hand, I divide the modulus by 2. So the dynamics is like that. So this is the Riemann sphere. Okay, this is a circle of radius 1. Here. And when I look at the dynamics, I divide the modulus by 2, so this point is 0. Here it's infinity. So I divide the radius by 2, and I double the angle. Okay. So if you fix some epsilon, And you look at z less than epsilon, and you iterate. What happens is after some time, you end up in this disk of reduced epsilon. And then you, at scale epsilon, you don't see anything happening. At scale epsilon, everything is squeezed, okay? Okay, so if you start from the disk of radius 1 and you apply the dynamics in a finite number of steps, which depends only on epsilon, you enter in this zone here, this region where you don't see anything at scale epsilon, okay? Okay, so there is also like a ball of radius epsilon here, and then the dynamics is like that, and you double at each time. Then you can show that the topological entropy is 0. Okay, so this I let as an exercise. Okay. But basically you cover the sphere minus a disk of radius epsilon centered at 0 and a disk of radius epsilon centered at infinity by balls of radius epsilon. Okay, so you need roughly epsilon square balls like that. And you will not see more orbits than this times finite number. Okay. So the entropy is 0. So the topological degree is 2. The map is just continuous. It's not C1, the entropy is 0. Okay, so now I want to stop talking about continuous and differential transformation. I want to come back to the subject of this conference. So, I don't know. I would say yes. I'm not sure. I mean, when I say I'm not sure, I say I'm not sure it has been proven. Depends on what you call piecewise C infinity. You need to be careful. This one, in some sense, is piecewise smooth because you just in C you can cut the plane like that, and you have a singularity which is hidden in the border of a piece. Okay, so you need to be a little bit careful. Now this, from here to here, I mean, you double the angle and you reduce. It's piecewise smooth, but you maybe not up to this point. You need to be a little bit careful. Okay, but yeah, maybe we can discuss this not after, but maybe tomorrow or a day after, because I need to think about it. Okay. Okay, so now I want to move to algebraic dynamics. So iteration of regular endomorphisms of projective varieties. So let's say projective varieties over C. And in fact, the result is more general than that. It's due to Gromov. Okay. So it's 3. And it says the following. So let f from x to x be regular endomorphism. Okay, so I'm just saying that it's regular. So if I want to talk about maps from x to x which are not regular but rational, I will say rational transformation. So I will never write regular again. of, so I will write smooth here because I will give the proof when it is smooth, because I will use differential geometry, but it works even if the variety is singular. Complex projective variety. Okay. Then we have an upper bound for the topological entropy. And here I insist again, so it's a transformation given by X on the complex set of points. Okay, so this is a compact set, and I look at the topological entropy in the sense I defined previously. So it's a smooth map on a compact set for the usual, I would say, topology of manifolds. So I will use the vocabulary Euclidean topology. Yeah, topology from differential geometry, not the Zariski topology. Yeah? Okay. And this is bounded from above by what? Max for P of the log of lambda P of F. Okay, and this is the pth dynamical degree. I will give a definition of it in a few minutes. In particular, this is less than log of rho of F star. Okay, so for F acting on the cohomology of the manifold X of C. So by Yomdin theorem, we get an equality. See, if I apply Yomdin theorem, here I have an upper bound, but I had a lower bound, so I have equality. Okay, and then there is a second statement which is due to Dean and Sibony. The upper bound holds for a dominant rational self-maps of X, okay? But then I need to explain what I mean by entropy of rational maps, okay? So this means that, again, the topological entropy of F on the complex points is bounded from above by max over P of the log of the lambda P. So again, these are the dynamical degrees as defined by Charles Favre last week. And here, what is the topological entropy? So for topological entropy, I was considering for the definition continuous maps from compact set to compact set. But a rational map has indeterminacy points, so it's not a continuous map. Okay? But what you can do is you can apply the same definition. So you want to count the number of orbits you see at scale epsilon during time n and look at the exponential asymptotic growth. You just look at orbits which are well defined. In this counting process, you just consider orbits which do not visit the indeterminacy locus. And this is a definition of the entropy. Okay? Okay, so we have this upper bound, but there is no lower bound like the one given by Yomdin theorem in this context. Okay, so okay. So again, if you call this number the entropy of the map, it's not very good. Okay. This number, it's good to call it the algebraic entropy or the numerical entropy or the homological entropy, but not the entropy or topological entropy. Okay, so the example here to show that the lower bound does not hold is like that. It has been given last week by Favre's example from last week, which in fact is due to Vincent Gage. There you take, you start with the map from P1 times P1 to P1 times P1, which is, let's say, X, Y, goes to X plus 1. So I use affine coordinates, let's say Y square. Okay? It's a regular map. This one is regular. You see, it's just a product map. On P1, I do a translation. On the second coordinate, I just do Y goes to Y square, which is a polynomial endomorphism of P1 times P1. This map, I can apply Gromov Yomdin. The topological entropy will be log of 2. Okay? This one has 0 entropy. This one, we did the computation on the unit circle, but it's the same on P1. It's log of 2. Okay. But now I conjugate this transformation by a birational map which contracts what happens at infinity on the x coordinate. Okay. So every orbit goes to infinity times P1. Okay. When n goes to infinity, x plus n goes to infinity. And so the point that go to the fiber above x is infinity. And then you do a birational transformation to blow up the origin here, which is fixed by this map, and then contract you do this, how do you call that, Jeremy, this Sarkisov link of type, I don't know what, okay? And then you can somehow squeeze completely the dynamics into a fixed point, okay? But the map is just rational. Okay, so I will not give more details because it has been done last week. Okay. What do I want to say? Okay, so this is a theorem I want to prove above there. So I want to prove the upper bound. And let me state it differently. Let X be a compact scalar manifold, let f from x to x be a holomorphic transformation. Okay. Then the topological entropy of f is bounded from above and equal by Yomdin to the log of the spectral radius of f on the cohomology. So let me give the best statement. It's the max over p of the log of lambda p of f, where lambda p of f is the spectral radius of f star on the piece of the cohomology, which is the Dolbeault cohomology group HPP-XR. Okay, so it's a part of the cohomology which is invariant under the action of f. You compute the spectral radius on this part. You define lambda p like that. In fact, in the case of complex projective varieties, this definition of lambda p coincides with the topology, with the dynamical degree defined last week. But said like that, I'm using, here I'm using the Hodge decomposition and the Dolbeault cohomology group, and this works for all compact Kähler manifolds. So this gives a statement which contains that one. Let's say I will put smooth here. As a particular case. Okay. And in fact, the proof of this particular case really, uses Kähler differential geometry, Riemannian geometry, and so this is the right level of generality. Okay. So this is the proof I want to. This is the theorem I want to prove tomorrow. Before I do that, let me add some remarks. Okay, so I will explain what a Kähler manifold is. I think I will define everything which is involved in this statement tomorrow. I will also explain why this lambda p coincides with the definition of dynamical degrees given by Charles Favre last week, but this I will do tomorrow. Okay. What I want to do in the few minutes which remain is discuss some consequences of this theorem. And it's just some kind of ideas that you can get from this theorem, and then I will state the right statements coming from these ideas. Okay. So the first idea is the following. You see, the topological entropy of f is bounded from above by the maximum of the modulus of the eigenvalues that you see for f on this part of the cohomology. Okay? But on the other hand, by Yomdin, it's bounded from below by all eigenvalues you see on the whole cohomology group. So we should be able to give an upper bound for these eigenvalues on the remaining part of the cohomology. Okay. This follows from Gromov's theorem. If you have an eigenvalue on the cohomology group, alpha, its modulus is bounded from above by an eigenvalue that you can see on HPP for some p. Otherwise, there will be a contradiction between the Yomdin and the Gromov theorem. Okay, so what is the right statement? So this is due to Yomdin. So first, I need to recall what is Hodge decomposition theorem. Okay. So if you look at the cohomology of X, so X is X of C. Okay, it's a real manifold that you get when you take the complex points of X with complex coefficients. So then you can decompose it as a direct sum. So you get the sum for P plus Q equal to K of H, P, Q, X. Okay, so this is called Hodge decomposition. And what are the HPQ? One way to think about it is, let's say, Dolbeault cohomology. You can take differential forms of degree P plus Q, okay, which are of type PQ. Means forms like that. Sum of A ij of Z, dz I, which J bar. Okay, I will give a concrete example like that. So this is a smooth. And these are complex coordinates, and what I denote by Z to the I is Z1 to the I1. I mean, let's say wedge dz2 to the I2, wedge dz, let's say, m to the im, where m is a complex dimension of X. Okay. And similar notation for dz bar to the j. And you sum over what? The length, which is the sum of the ik of I is P, and the length of j is Q. Okay, so these are differential forms that you can write like this locally in complex coordinates. Closed one modulo exact ones. So let me give a concrete example. For instance, H2 of X C is H20 plus H11 plus H02. And here you can, so this is H2 of X with integer coefficients, and you tensorize by C. So you can look at complex conjugation, and complex conjugation permutes this and acts here. So the arrow, the red arrow, are what you get by complex conjugation. You see, if you take a form of type 2,0 and you complex conjugate, you get a form of type 0,2. Okay, and in fact, here H11 inherits some real structures. It is, you can define H11 with real coefficients, which is a set of fixed points of complex conjugation, or if you prefer, intersection with cohomology with real coefficients. Okay. And so the HPP are defined similarly. Okay. So HPP is the middle part in the Hodge decomposition when you look at the cohomology group given by forms of degree 2p. Okay. Okay, so you see, what Gromov's theorem tells you is that in this decomposition, you only have to care about what happens on H11, H22, H33, so the very middle part of the cohomology. But you have all the rest, you know, for instance, H20 or H31 and so on. And the eigenvalues on this part of the cohomology should be controlled by what happens on the middle part. And the theorem by Dean is that the spectral radius of f star on h pq, okay, so this you can call lambda pq, is bounded from above by lambda p times lambda q, square root of that. Okay, so this one is, with this notation, lambda p is just a shortcut for lambda pp. And the idea of the proof is quite simple. You let f act diagonally on x times x. Okay. Then you take omega, a form of type PQ on X. Okay. And then you get, so you have two projections, pi 1 and pi 2 from X times X to X. And you take the form pi 1 star omega, pi 2 star omega. So you get two PQ forms on X times X. You take the complex conjugate of that. So this one is of type pi q, and this one is of type, QP. You take the wedge product. It's of type P plus Q, P plus Q. On X times X. Okay, and it is not zero. Okay, even cohomologically. Okay, so it's a way to start with something which is of type PQ, and to end up with something of type P plus Q, P plus Q. Okay, and then you use what happens, I mean, for forms of degree P and forms of degree Q, using the same trick to compare what happens, and you get this inequality. And once you have this idea, it's quite easy. Okay, maybe I have to stop now. Yes, no, I don't remember when I should stop. Okay. Okay, that's it for today. Yes. So I throw it to you, and you throw it to above.
Is that on? Yeah. Okay. So, for one of the exercises you had earlier about when you have a compact manifold and a Lipschitz continuous map, and you give a bound by the dimension times the log of the Lipschitz constant, you said that you want X to be a manifold so that you have a definition for the dimension. Is there actually a proof if you have just the topological dimension?
Yeah, yes, like, I don't remember exactly which dimension you need, but
Right.
so I don't want to give, yes, but there is a proof that you put
Right, so.
the right notion of dimension.
Okay, thank you.
Okay.
More questions?
I think the notion of dimension, just by looking at
Sort of refinements.
dual, I mean, the simplicities you get, by looking at intersections of open coverings is
Yes,
not
this is the one I'm
sufficient. This
thinking
one
of.
I think is not sufficient, but maybe Hausdorff dimension should be there or something.
Oh, okay, okay.
Yes? Maybe we can apply the strategy I proposed last week. When you give a question, we call your name so that we know each other. Otherwise, after 3 weeks, I will not know who is who. So what's your name?
Jiarui Song.
Yeah.
Okay. Does the upper bound of the topological entropy holds for F is correspondence?
I think yes. Yeah, yes, I think so. Yes. So the proof I will give for this one, you will see it holds for correspondences, such that the two projections are good. I mean, I mean, regular things. I'm saying something. In fact, what I'm saying is a little bit wrong. But yes, it works for correspondences. But then you have to define what is this number correctly. Yes. So to make it short, I think it works for correspondences. I'm not sure it has been written, but if it has been written, it's by Dean and Sibony, or Dean and his collaborators. Actually, it's a very good remark because, you know, the point is that if you start with a compact, I mean, let's say a smooth complex projective variety, usually there are no regular endomorphisms except, let's say, constant maps or the identity. I mean, there is no, dominant endomorphism except the identity for generic, at least for generic hypersurfaces in Pn of degree large enough, at least n+1, this is easy to prove. But there are a lot of correspondences, and from time to time there are a lot of rational transformations. So the right setting for this type of questions is usually correspondences. This is a good setting. But people that start with the easiest cases first, and this is what I want to